Hello everyone, wherever you are in the world, and welcome to our webinar about decarbonization solutions for ironmaking. We all here are appreciating that you're joining us and giving us the opportunity to present our circular process for carbon-free direct reduction of iron ore. My name is Max Köpf and I have the pleasure to be your host for this webinar. I'm responsible for technology and R&D in the business line Ferrous and Heat Transfer, and have been working in the last 20 years in Metso Outotec and its predecessor companies in different functions, roles, and even locations, but always with a strong focus on our ferrous technology. Our agenda for the coming hour is as follows. After some practicabilities, we will shortly introduce the strong focus on sustainability in Metso Outotec's metals processing technologies. The main part of this webinar will be the presentation about Circuret as a process Ironmaking, and which has already proven its functionality. After the presentation, we will have a Q&A session to discuss your questions and comments. Before the presentation, some guidelines to ensure a smooth realization of our webinar. The obligatory and well-known disclaimer is emphasizing that the information in this webinar is provided for guidance only, and warranty of any kind is of course excluded. Our webinar is planned for 60 minutes. We have foreseen 50 minutes for our presentations and then another 10 minutes for our Q&A session. This webinar will also be recorded. A link to the meeting recording and the presentation will be available on our webpage in the coming days. If you have any questions, please post them during the webinar and we will answer them during the Q&A session. If we run out of time before replying to all of your questions, we will answer them in the next days by email. Posting of questions is easy. You simply type the question in the chat box and submit it by clicking the send button. In case you're experiencing any technical difficulties in the webinar, please refresh your page or exit the webinar and rejoin. The slides of the presentations are already now available for download by clicking on the icon in the tool as shown on the slide here. But now we want to begin with our presentations. Firstly, I want to ask Jari and Ataul to give a short introduction in the priority of sustainability of Metso Outotec's metal processing technologies. For those of you who don't know the two gentlemen, Jari Algas is the president of our business area metals since 2020. Before that, Jari was already 5 years with Outotec and served as CFO since 2015. Ataul Ahmad is the vice president of our ferrous and heat transfer business line at Metso Outotec. Before that, Ataul has been a successful entrepreneur and an accomplished supply chain leader in automotive, gas and oil processing, and mining industries. But now I would like to hand over to Jari. Please.
Please, Jari, unmute yourself.
Yep. Okay, now I think you can hear me. Is that so?
Yes.
Good, thank you. Okay, welcome also on my side. I will take you through this metals for a healthier planet as a starting point here before we go into decarbonization solutions for iron making. So pleasure to have you here. So if we go to the next page, please. We in metals in Metso Outotec are really having a broad technology portfolio. We have leading process technologies for metals producers. So if we look at our portfolio, we have comprehensive solutions and services for pyrometallurgy, sulfuric acid, and agglomeration, as well as heat transfer solutions. We are the one which are bringing the most decrease to CO2 emissions to our clients here, supporting our customers to reach their sustainability targets. So over 7 million tons per annum, we are able to save CO2 emissions for our clients. And that we are doing with a number of technologies, but to name a few, the biggest drivers to help our customers handprint is copper flash smelting, alumina calcination, as well as ferrochrome smelting. The industries we serve are base metals, iron and steel, precious metals, light metals, and fertilizer. And currently, as I guess all of you are aware, there is a strong market demand for metals processing solutions, which we've also been able to show in our order intake during the last quarters, what we have been presenting. Go to the next page. If we go more into what references we have available, in iron ore agglomeration, we have over 400 sinter plants and 140 pellet plants in traveling grade and grade kiln technology supplied, including the world's biggest ones. So if you really have need for a big pellet plant, the biggest in the world, come to us. Light metals, we have over 70 alumina calcination and tube digestion plants delivered. And then also in smelting, we are the industry leader. We operate the world's largest copper, nickel, and ferrochrome operations, and we are also widely used in various secondary smelters. Over 60% of global pyrometallurgical copper and nickel are produced with our technologies. And around 60% of global ferrochrome is produced with this technology, what we have available. And we have also delivered 100 anode casting shops. If we go into the right-hand side of the presentation, acid plants, we've delivered over 650 acid plants to date with high efficiency gas cleaning solutions. We have the largest metallurgical acid plant delivered to date, 4.5 tons per day. And then also the largest sulfur burning plant to date, 5,000 tons per day. And in the fluid bed side, we've delivered over 300 fluid bed roasting installation, again, including the largest partial roasting plant in the world. And in the calcining, we've delivered over 150. Okay, now we already changed page here, 150 plants over time. If we then look at major metals processing orders we published since the merger, we've gotten an order for a zinc plant expansion of 150 million euros in Norway quite lately. We've also gotten a 90 million order for a nickel smelter modernization in Russia. And obviously the biggest order ever for the company, a 360 million euro order for a copper smelter to Freeport Manyar in Indonesia. And 6 iron ore pelletizing plant as well as 2 alumina processing plant. And this, to specifically see where they are situated, we talk about China and India, which I consider the 2 most competitive plant in the areas in the world to deliver plants, and that we've been able to achieve orders in this area means we are also very competitive. We don't only have the leading technology, but we can deliver it in a competitive way. On top of that, we have the precious metals recycling plant, which really shows we are also delivering the state-of-the-art in the newest of solutions, which is recycling plants. If we go to the next page, please. If we look at the technology development, we see today that global megatrend drive development. We talk about electrification, sustainability, digital transformation. Some of the things we also have to consider is delivering it in a modular design with digitalization, and as said earlier, product competitiveness as service, which is a basis to have this leading edge offering what we have today. And then having differentiation to strong intellectual property and process development, because really to be a leader, and if we look at our development, we really have kind of 4 things that really stand out. Either we have the highest yield, use the least water, use the least energy, use the least emission, or then we have all 4 of these in the same product or process we are offering. We go to the next page, please. If we look at the development we have going, carbon-free production is very high on the agenda at the moment, and that's also something you notice in in the news with, if we look at carbon-free steel, what you will hear more about here going forward, but also carbon-free base and light metals, next generation pellet plants, as well as gas cleaning solution, just to name a few of the areas where we are spending money to develop products for your use going forward. And as you can see here on the right hand side, we are saving over 7 million tons of CO2 emissions for our clients annually. And 100% of our R&D spend includes sustainability targets, because as you are aware, sustainability is something which is here to stay and will continue, and we want to be a leader in this. If you go to the next page, please. Here I hand over to Attal, so thank you for the time being.
Thank you very much, Jari, for having this detailed over our metals business. And I will now go more deeper also into our ferrous and heat transfer business, and then hand over to Dr. Sebastian Lang for our webinar, basically for the Circuret process. So if you look, we as a Metso Outotec have been always a technology company with all our predecessors. If you look to the history, we tried to develop new groundbreaking processes, but then also these processes became industry state-of-the-art products or technology. If you look for in the history, we have here some examples as shown. So this is also to make you a little bit familiar that we are developing new processes, and you are with us on the right side. If you, for example, look, we have developed the sintering, was developed around 1910, and then we came with the flash smelter for copper and nickel concentrate in the 1949s, and then we came with our iron ore pelletizing in the 1960s, and then with the circulating fluidized bed process for alumina calcination in the 1970s. And already the Circuret, we have already developed, or some decades ago, 2 decades ago already, the Circuret direct reduction process for iron ore fines and of the last millennium. But at this time, it was not the right time to introduce this to the market. The world was not ready for decarbonization, but now it is the right time, and we are now introducing this technology to our customers. But we did not only develop these new processes, we kept them over the decades in the status of best available technology. So we always upgraded them by continuous development. We respond to the challenges of the industry and the society in the respective period of time. If we look to this, in the beginning, the main focus was more to increase the capacity. Then in the 70s, to look more for energy efficiency. Then later, reduction of emissions, for example, of dust or SO2. And then in the last decade, we strive for digitalization. And today, I think we all agree here on the call and the webinar that for the biggest challenge for our planet is the climate change. And we need to reduce the CO2 footprint drastically. And if we, in the steel industry, we are a big part, and we can contribute a big part onto this. If we now looking to summarize here, clear focus going forward on electrification, sustainability, and digitalization to drive the industry. Decarbonizing the industry is our joint target. And then metals business as Metso Outotec has strong focus on carbon-free production. You have already seen our solution, and now we as metals stand for a healthier planet. And now I will hand over to Max. He will introduce our Dr. Sebastian Lang. And Max, up to you. You need to unmute.
Okay. Thank you, Jari and Atol, and sorry for the technical problem. Now I want to introduce Sebastian Lang to you, who will present the technical content of our webinar and introduce the Circuret process to you. Sebastian Lang started his scientific career at the Virginia Tech in 2009 and received his PhD in 2015 from the University of Technology in Darmstadt. After his time as research associate at the Institute for Thermal Process Engineering, he joined already Metso Outotec as a process specialist and is today responsible within the product group Ferrous as director for business development and modeling topics. Sebastian, the floor is yours.
Thanks, Max, for the kind introduction. A warm welcome also from my side. I have the pleasure to guide you through the technical part of today's webinar on Circuret, Metso Outotec's hydrogen-based direct reduction technology for fine ore. Within the next 35 minutes, I would like to give you an overview of the Circuret technology. After my talk, we will have some time to discuss questions, which you can type into the chat at any time. To set the scenery for Circuret, we can shortly revisit the decarbonization challenge. Then I would like to introduce the process principles of Circuret before we can have a look at the industrial demo plant which was built some years ago in Trinidad. Then we can have a quick look at Circuret in combination with smelting and the question how to deal with degrading ore qualities. And before we come to the Q&A, I would like to give some insight into our R&D capabilities in Frankfurt. With the pandemic still catching everyone's attention, my impression is we have an elephant in the room. The realization process of how big the whole climate change issue is has started, and the more and more countries, but also companies, have set ambitious carbon neutrality targets until latest 2050. The global steel industry has a significant contribution of 8% to the overall carbon dioxide emissions, which is no wonder, as the basic blast furnace route is dominating the market share and emits almost 2 tons per ton of steel, with coke ovens, sinter and pellet plants, all based on fossil fuels. To face the decarbonization challenge, innovation is needed and breakthrough technologies must be implemented. With Circuret, we have such a technology at hand. Circuret is a 100% hydrogen-based direct reduction process for fine ore, omitting the necessity for agglomeration. Any hydrogen source can be used for the process, which is colorblind in that sense. But obviously, green steel comes from green hydrogen. The product DRI or HBI does not contain any carbon. Nevertheless, it can be used in EAFs for steel making, which was successfully shown in industrial trials in the past. The technical feasibility of the process has been proven in an industrial scale demo plant in Trinidad at the beginning of this millennium. Let's have a look on the process principles, its development history, and why fluid bed technology has such a nice fit to iron ore reduction based on hydrogen. From a historical perspective, hydrogen was an enabler for the direct reduction in fluid bed reactors. As early as in the 70s, direct reduction in the fluid bed was introduced, but suffered from problems with particle sticking, material buildup, and frequent shutdowns caused by the high temperatures needed for reduction under carbon monoxide. Own research in the 90s revealed a healing effect when running the reduction on hydrogen, as the temperature could be decreased to avoid sticking. This was the starting point for the Circuret process development. On the next slide, I would like to introduce some fluid bed fundamentals. The proper particle size and size distribution is paramount for fluid bed operation, as fluidization depends on drag and gravitational forces, which are particle size dependent. The Circuret process works in principle with very fine material from 10 micron up to a particle size of 8 millimeters. To achieve the optimal metallurgical outcome, the process involves, if needed, steps to narrow down the particle size distribution. Ultrafine material can be microgranulated, and too coarse material can be crushed by mechanical or thermally induced forces before fed to the metallurgical core plant. The core plant consists of a circular fluid bed reactor, CFB, and a stationary bubbling bed reactor, FB, to account for the special nature of the iron ore reduction. The reactor types are further explained on the next slide. Here we can distinguish between 3 reactor systems, which are all part of the Circuret process. The bubbling or stationary fluid bed is characterized by low gas velocity and a sharp interface, which forms an apparent bed surface. The carryover is limited. Slip velocity and throughput are low, which means that the reactor system is well suited in case that prolonged residence time is required. In contrast to this, a circulating fluid bed reactor has a high gas velocity with a high solid entrainment and recycling rate. Intensive mixing and excellent heat and mass transfer make it an optimal reactor for fast reactions with short residence time requirements. The transport or flash reactor has a high solid entrainment caused by very high gas velocities. It does best what its name suggests, pneumatically transporting material. As it provides still decent heat transfer rates, we use it as a flash heater in the process. The next slide shows nicely why these reactor types are ideally suited for iron ore reduction under hydrogen. The kinetics of the iron ore reduction are really fundamental to the Circuret process. The overall reaction from hematite to metallic iron is shown up here. In reality, this is a sequential reaction network from hematite to magnetite to woostite and then to metallic iron. Observing the reduction degree over time, one can distinguish 2 regimes, which are shown here on the graph. The first one, with fast reaction rates and a reduction degree of about 70% within 20 minutes, which is then shifting into a slower second reaction regime, which is controlled by intraparticle diffusion, indicated here in red on the graph. The 2-stage reactor setup of first a CFB and a downstream FB is adapted to this reaction characteristic and optimized in regard to the residence time requirements, with minimal reactor sizes and hence minimized capex as a result. As mentioned earlier, hydrogen is an enabler for the fine ore reduction, lowering reaction temperatures and omitting sticking. Operating at elevated pressure of around 4 bars reduces the gas volume substantially. This helps to decrease piping and equipment size and therefore investment cost. It has no effect on the thermodynamic equilibrium of the reaction. Nevertheless, it helps to remove the product water from the recycled hydrogen gas via condensation. How these fundamentals translate into an industrial process is shown on the next slides. Here we have a block diagram of the industrial process. Solid flow is indicated in red, gas flow in blue. Thermodynamically, the reduction reaction is highly endothermic, which means that we have to provide heat to drive the reaction. This is achieved via the sensible heat of the gaseous and solid reactants. Therefore, the fine ore material is fed into an atmospheric preheating stage. In case of magnetite as feed material, the material gets also oxidized to convert the dense mineral structure to a better reducible state. The hot ore is then fed at elevated temperature into the metallurgical core part, consisting of CFB and FB reactor. To create a closed loop system for the hydrogen, a process gas treatment sits aside, removing product water and dust. The metallized DRI gets downstream discharged to a briquetting section to produce HBI ready for shipping or smelter charging. Looking at the overall flow sheet, we start out with the metallurgical core of the plant, the two reactor stages. The CFB is fed with hot iron ore and receives fresh hydrogen and dust-laden gas from the FB reactor. There we have excellent mixing, which drives the reaction within 10 to 40 minutes at around 630 degrees, always depending on the nature of the ore, to the desired reduction degree. For final metallization, the solid material is discharged to the FB reactor, giving it the required residence time and a high thermodynamic driving force via the fresh and hot hydrogen to reach metallization degrees above 93%. The overall reactor setup is mimicking a countercurrent process to harvest its thermodynamic benefits. Zooming out and showing the full plant, a few other things become evident. We can see the ore preheating system on the left, which is also a CFB arrangement. We have the bucket elevator lifting the material up for feeding into the CFB and discharging it to the FB reactor. We have the gas heater for the recycled hydrogen. At the upper right, we have a section dealing with the gas treatment, first recuperating heat from the process off gas via a heat exchanger and then removing dust via a multiclone. The dusty material is then blended with the product stream to minimize production losses. The remaining dust and product water get removed by a scrubber system. The hydrogen gas gets then recycled back into the process. The hydrogen bleed is used as fuel for heating purposes. The highly metallized DRI gets discharged from the second stage reactor and superheated by the flash heater to appropriate temperatures for hot briquetting to produce HBI, or alternatively, the material can be directly charged to an EAF for hot beneficiation. We had mentioned the option for microgranulation, which is shown on the next slide. In this case, ultra or pellet fine concentrate is fed together with a binder to a mixer and subsequently microgranulated under some water addition. This process variant brings the advantage to recycle the dusty material reclaimed by the scrubber system. The green granules get then fed into the preheater for hardening. The downstream process route remains basically the same. Let's summarize the process here and name some consumption figures. To produce a ton of HBI, it needs 630 normal cubic meters of hydrogen, 1.5 tons of ore, 750 kilowatt hours heat, and about 130 kilowatt hours of electricity. All typical ore types can be used. For merchant HBI, the iron content needs to be above 66%. The preferred grain size should be in the range of 100 micron up to 2 millimeters. If substantially finer, microgranulation can be applied. For coarser material, size reduction is needed. Hydrogen is the only reductant in the process, regardless of its origin. For preheating, any fuel can be used. Future process variants will be fully electrified. Nitrogen for purging and inertization is a consumable and needs to be considered in the balance of plant. Now, benchmarking Circuret against other steel production routes is certainly interesting for you. So let's have a look. To have a fair comparison of different steelmaking routes, we chose the battery limits to cover the whole value chain from mine to crude steel. All unit operations are included in terms of energy, cost, and emissions. On the left-hand side, we have the classical blast furnace route with a pelletizing step up front for agglomeration and a basic oxygen furnace downstream to process the pig iron. In the middle, we have the process route via the shaft furnace, also with a pelletizing step upstream and an EAF downstream to melt the DRI. On the right-hand side, we have the Circuret process, either fed with fines or microgranulated fines. The hydrogen comes as state-of-the-art variant from steam reforming. In future, green hydrogen can be used in a process variant that we call Circuret Plus. Also, heating is fully electrified to omit any fossil fuel requirements. The DRI gets also melted downstream in an EAF. After clarifying these process routes, let's have a look on the benchmark figures. The table here shows the results of a techno-economic analysis. The model was used for this. The model we used for this is based on some assumptions shown here on the right. Worthwhile to highlight is the price for carbon taxation of $40 per ton, the fine ore price of $120 per ton, and the pellet premium price of also $40 per ton. These figures are rather conservative, I would say. The predicted future hydrogen price of $1.5 per kilogram is based on the predicted electricity price of 2.5 cents per kilowatt hour. These last future predictions are only taken into account for the Circuret Plus process variant. First, let's have a look at the carbon dioxide emissions. The blast furnace value chain is here emitting the most, with 1.8 or actually 2.5 tons per ton of crude steel when neglecting the credits from electricity production, which will probably be the case once the grid is mainly fed with renewable electricity in future. The blast furnace is followed by the shaft furnace route with slightly above 1 ton per ton of crude steel. Even based on steam methane reforming, Circuret can lower the carbon dioxide footprint to 0.9 tons per ton of crude steel, which is about half of the blast furnace route today. Circuret Plus with electrified heating gets basically down to zero. The 200 kilograms per ton of crude steel are still emitted by the carbon addition to the EAF smelter operation. Looking at the production cost and the pie charts indicating the cost breakdown, it becomes evident that the blast furnace is highly suffering under the carbon dioxide taxation. Circuret today has a slight benefit in carbon tax compared to the shaft furnace. But the competitive edge comes mainly from omitting the pellet premium cost, which weighs on the shaft furnace route. Under the given price assumptions, Circuret Plus would only be slightly more costly than Circuret today. Comparing the electricity consumption, the gas-based direct reduction technologies, Circuret and the shaft furnace, require quite some electrical energy for compression of the process gases and for the smelting in the EAFs. Circuret Plus, as electrified version of the process, is substituting fuel by electricity. The high requirement there is not a bug, it's a feature. This is also reflected in the low fuel consumption figure of Circuret Plus of only 8 gigajoules per ton of crude steel. Circuret today and the shaft furnace have comparable fuel consumption figures. The blast furnace requires a bit more energy, as this is not a closed loop system in regard to the reductant. After this rather theoretical exercise, let's have a practical look into the field and revisit the industrial demo plant operated in Trinidad around the year 2000. This plant was designed for hematite ore from the Carajás deposit in Brazil. The particle size between 100 micron and 2 millimeter was ideally suited and could directly be fed to the process. The product, zero carbon HBI, was shipped to the US market for smelting in EAFs. The design capacity was 500,000 tons per year. Today, we see an economical size for a single line at 1.25 million tons per year. Several lines can be built, sharing a common balance of plant like hydrogen production or air separation facilities. Building and operating a first of its kind plant has always challenges and comes with learnings. At the end, it were not the teething problems which led to the final shutdown of the plant in 2005, but rather the market and political circumstances on Trinidad during that time. The experience and learnings that we took from this plant are invaluable and the basis for today's design. Here is a top view of the plant. The core plant itself had quite a compact footprint with 100 times 60 meters. Material was delivered from the day bin and transported to the preheater. You can see the bucket elevator, then the reduction plant, and on the left, the hydrogen steam reforming plant. Another view of the plant. Again, the day bin, the bucket elevator can be seen. You can see the gas heaters. To the left then, the briquetting and fines recycling. If you ask me, this plant was erected 20 years too early. Today, the market drivers have dramatically changed, and direct reduction based on hydrogen makes more sense than ever before as a solution to the decarbonization challenge of the steel industry. Talking about industry challenges, another challenge is connected to the declining ore grades, which brings us to the concept of hot beneficiation. DR grade ores are scarce, and the market will have to find a solution on the question how to process BF grade ores. Single stage Circuret in conjunction with a smelter provides an approach there. Circuret fits into a bunch of different scenarios. For DR grade ores, the standard two-stage Circuret process is well suited. We have discussed that before. Then direct feeding to EAFs or as additional burden to blast furnaces is applied, helping them to reduce their emission footprint by some percentage points. This will be interesting during a transition period. For low BF grade ores, a single stage Circuret process in conjunction with a smelter is the proposed option here. This comes with reduced complexity and a lower capex requirement on the Circuret plant. The pre-reduction degree in the CFB can be adjusted to meet the requirement from the smelter. Around 80 to 85% is possible without too much jeopardizing the reactor size. Following this hot beneficiation approach, the pig iron can be fed into an existing steel production route, which continues downstream with the basic oxygen furnace. From an investment perspective, This prevents this acid from stranding and substitutes only the highly carbon dioxide intensive steps of sintering and coking, keeping the rest of the steel mill's production chain alive. We can have a look at this simplified flow sheet on the next slide. As mentioned, here we are operating the metallurgical core plant only with a single stage reactor setup for low-grade iron ores. The reactor design is adjusted to reach the requirements arising from the smelter operation. The product is pig iron, and the impurities in this hot beneficiation concept get separated in the smelter via the slag, which can be a potential side product for the cement industry. The flow sheet is simplified as some of the hydrogen gas heaters, briquetting machines, and flash heater are not required anymore. With this concept explained, I'm already coming towards the end of my presentation. But I do not want to miss the chance to highlight shortly our R&D and pilot plant capabilities in Frankfurt. We have a long history in experimental research, and this year we actually celebrate the 85th anniversary of the site in Frankfurt. You're all welcome to visit us there. The gray building in the background is a 700 millimeter fluid bed pilot plant, the biggest that we have there. Our typical approach to check the applicability of certain customer materials to our Circuret technology is shown on the next slide. Besides standard material characterization via XRD, XRF, wet chemical iron analysis, and particle size analysis, we start testing the material in a 50 millimeter small scale batch reactor to get a first idea about the reducibility of the material under certain process conditions. We then increase the size of the test reactor to 80 millimeter, running the process continuously and under pressurized conditions. From these tests, we can already derive first design information for equipment and plant sizing. Test work in a 200 millimeter reactor setup is complementing the scale-up process for the reactor design. This gives also the possibility to produce enough product to pilot test unit operations like hot briquetting or smelting downstream. The overall scale-up process is accompanied by the application of simulation models to transfer the gathered experimental information into an optimal industrial plant design. Now, finally, I want to summarize my talk here on this last slide. Hydrogen can completely substitute fossil fuel as a reductant and is therefore a possible way of decarbonization and lowering emissions. Energy and cost-intensive iron ore agglomeration is not required and gives Circuret a competitive edge compared to the shaft furnace route. Produced HBI or DRI can directly be used as feed materials in EAFs for green steel making, as soon as green hydrogen is provided. Even on classical steam reforming, Circuret saves 50% of the blast furnace route emissions right away. Single-stage Circuret allows to process low-grade ores in a hot beneficiation concept with a downstream smelter. With all this, Circuret is a possible step to carbon-free steel production in the future. Thanks for staying tuned, and I'm looking forward to discussing the topic with you.
Okay, thank you very much, Sebastian. And now we are already on the Q&A part of our webinar. And we have already received several nice questions. Just a reminder, if you want to raise a question, you still can do it. Simply type it in the chat box and you submit it via clicking. As already mentioned, we want to have Sebastian here. I have here, I would say the first question is for you. What is the minimum annual capacity of a circuit plant? We talked about the biggest one on a commercial basis.
A minimum capacity.
A minimum.
Scaling the process down, that's an interesting question. In that regard, I would say there are no limits. Yeah, I mean, scaling it down, you would end up basically at a laboratory scale. Yeah, so I would not see from a technical perspective a limitation there, but from an economic perspective, of course, there the question that would have to be investigated in detail to find out if it makes economically sense, because the economy of scale, of course, is working here as well, and we would not say, let's say, our investigations have shown that the economical size is at about 1.2 million tons a year, but needs to be discussed in detail. Interesting question.
Yeah, I would say it very much depends also on the application. For HBI production in the steel industry, of course, we have the economy of scale. If we have any application for the treatment of waste materials, of residues, then there's a completely different business case. And then we planned plants of 300,000. We have the Trinidad plant of 500,000 tons per year. So it really has to be seen in this regard.
Yeah, depending on the business drivers, correct. Yeah.
You have a very interesting question for you, and I hope you can answer it immediately. Yeah. What were the main handicaps for circuit process in the last 2 decades where we were not able to go to the market?
Yeah. Yeah, I would say what happened earlier is a certain technological lock-in, and that. With the decarbonization topic now and the shift towards hydrogen, this market scheme is completely broken up again. And there we see that there will be, that's my opinion, certainly a need for hydrogen direct reduction, also for fine ores. And that's where we come with Circuret, and we have a solution there for the market.
Thank you. Here's a question. It was partly answered during your presentation. The question came quite early, but are there any limitations to the circuit process regarding the iron ore type or the grain size? And the more interesting part of it, what have you tested already?
Yeah. In regard to particle size, yeah, we explained that microgranulation is an option to let's say increase the particle size if too fine. I mean, we're still operating in a fluid bed reactor, and you can't trick the laws of physics. That's and we can do it as well. So it needs a proper size distribution. Yeah, and microgranulation gives the chance to increase. Crushing or thermally induced crushing can decrease the particle size. And in terms of iron ore types, I think we have seen most of the types that are present out there: magnetites, hematites, roasted materials, and always depending on the nature of the ore, but most of them we were able to reduce, and it's then a question of, let's say, having a detailed look and defining where we end up with the throughput at the end of the day, rather that it could then be limiting the application there.
Yeah, so the key message is it's not only what we had in Trinidad, with what was more or less a sinter feed, It is really also finer concentrates, finer material, which can then be treated by microgranulation to get the size distribution what we need.
Correct. And that we have tested intensively in the lab in the past.
I feel a question which is quite nice because it leads us perhaps to a normal process of a project development. What is the typical sample amount needed for tests?
A typical sample amount depends a little bit on the scope of the investigation, but for 50 millimeter, these first scouting tests per batch, only a kilogram of material is enough. So to have a proper test campaign there, it needs, let's say, 200, 300 kilograms. If we then move on into the bigger pilot plant setups, there it needs, let's say, between 1 and 2 tons of material to have then sufficient material to really continuously operate the pilot plant, and also depending on if you want to investigate downstream unit operations like hot briquetting and or smelting. That's then more driven by the demand of the downstream process, but 1 to 2 tons of material is already something we can have a nice investigation.
Well, and perhaps it's interesting or worth to mention that with the tests in the 200 millimeters test plant and with this 1 or 2 tons of material, we were able to design the plant in Trinidad several years ago to upscale it and made a plant which was then commissioned successfully and operated several times. Here's a question: what is the impact of low-grade iron? That means the typical sinter feed or blast furnace qualities of 62 to 33% of iron to the specific consumption of the circuit process?
To the specific consumption, as you are lowering the iron content or the iron oxide content, basically the specific hydrogen consumption goes down. Less reductant is needed in order to metallize that material. That is a main difference that I could see. In other regards, I would say heat consumption also a little bit lower, as we have an endothermic reduction reaction. Let's say on the utilities, I would say not too much change at all. So slightly lowering the consumption figures, that would be the consequence.
Okay, thank you. Here's an interesting one. If we look at the circuit smelter combination, do you think it makes sense to go to a lower metallization of the circuit and do the rest in the smelter? What would be an appropriate metallization after circuit for this combination?
We propose to have, let's say, a metallization degree of around 80 to 85%. At the end of the day, it's a trade-off, and it needs a techno-economic investigation to really define that. It needs a sweet spot. The higher you go in metallization rate, the higher your throughput on the smelter side becomes, the lower the throughput on the circuit plant becomes. And that trade-off needs to be balanced. But I would say around 80% is where we see that economic sweet spot. And maybe that's answering already the question here.
A little bit back to the history, and this is also explaining the story of Circuit in the last 20 years. When the plant in Trinidad was developed, the Circuit project target was to decrease the emission or to save the energy.
The target was to omit the cost of pelletizing.
Exactly.
And emission was already a topic back then, but certainly not carbon dioxide emissions.
Yeah.
And as explained, hydrogen in that setup was purely an enabler for the technology. Yeah, from the historical perspective, people tried to do the fluid bed reduction under carbon monoxide. This did not succeed because of the sticking problem that we had mentioned earlier. And hydrogen was then the enabler, yeah, the decreasing the reduction temperature, getting out of that sticky regime, temperature regime, really enabled the process and was the driver for that. Yeah, omitting pelletizing costs, yeah, and have as still the competitive edge.
Yeah.
Today and back then, compared to a shaft furnace route, is omitting the pelletizing agglomeration cost. That's the cost that you can directly avoid.
Here, one of a question to an interesting topic. The circuit HBI or DRI has zero carbon. The EAF wants or requires some carbon in its feed. Otherwise, we will not have steel. That's clear. So how will this be addressed?
Yeah, that's a good question. And I would say what it will need in future is virgin iron units. With the smelter operation mainly fed, or at least partially fed with scrap, you have to deal with the impurities in the melt, and therefore it needs fresh iron units, which can be a zero carbon HBI or DRI. Also today you have to add carbon units to the smelter operation. So in that regard, it's not a change from what is happening already today. Yeah, maybe the level of adjustment of carbon to the smelter might be different or might have to increase if you increase the share of zero carbon HBI. But the trials in the past have shown that this can easily be done. And I think this won't be an obstacle for applying such zero carbon HBI or DRI to smelters.
Okay, I see that we are running out of time. Just as a reminder, we will answer all of your questions later. We still have a big bunch. So I would say I take a last one, which come just in. How is Circuret better than the HIFA competition?
I'm not a specialist in that technology, but from what I see is that Circuret is more flexible in regard to the particle size and particle size distribution. With the aforementioned microgranulation option, we can make the material fit to the process, and that's, I believe, a big benefit of the Circuret technology, that we have that long heritage of agglomeration in the company, and we apply that experience there as well to Circuret, and can greatly benefit from that.
Yeah. Looking at the time, I would say that was the last question. I would perhaps only add Circuret has already proven its functionality in a plant of 500,000 tons. It's an industrial size plant. The quality was shown. It was already a continuous process, which is a difference. So we have the advantage to be far beyond the pilot plant or lab scale status, and can really base our further developments on this experience which we made already several years ago. Okay, I unfortunately have to stop the Q&A session. As already mentioned, the recording of today's webinar will be available on our website a few days after today. And so please share this information also with your colleagues which might be interested. Copies of the webinar are already now available or also can be found later on the website. If you have any further questions about today's topic or any other feedback, please get in touch with us. We are looking really forward to hearing from you. With the link on this page here, you can also subscribe for our newsletter, which has been published already several months ago with the first edition, and which will also in the future give an update about the latest developments in the area of ferrous and heat transfer. In this link, you also can find the, in the side page, you can find the link to the recordings. So to wrap up today's session, I would like to thank you all for your participation. We really very much appreciate your time, your thanks, and the thanks you too for all your questions. Once more, a big thank you to our presenters today, to Jari, Atol, and to you, Sebastian. We would like to wish you all success with your business, and we hope today's webinar has given you some ideas and indications for the future transition of our industry towards green steel. So thank you very much for joining our webinar. Stay safe, and perhaps we have one day again the possibility to get in contact or even meet elsewhere in the world. Thank you.
Bye-bye.